Hi there, my name is Ethan Parker. Welcome to Beginner Machine Learning. Today we will have Lecture 5 and we are certainly getting to the nuts and bolts here. Let's remember from Lecture 1 that supervised learning is one of the methods of machine learning, and today we will be focusing on supervised learning, regression. Let's start slowly. Remember, a machine learning model is a computer program that has been trained on a dataset to identify patterns and make predictions on new data by learning from the patterns it finds within the data, essentially acting like a mathematical formula that can be used to analyze and interpret information without being explicitly programmed for specific scenarios. It's the output of a machine learning algorithm after it has been trained on data, allowing it to make inferences on unseen data based on what it has learned. So these types of machine learning are the different ways or methods we can use to make things consistent. Supervised learning is a type of machine learning where we train a model on a labeled dataset. This means that for every input data point, we have a corresponding output label. The goal is to learn a mapping from inputs to outputs so that we can make predictions on new, unseen data. So what is regression? Regression is a type of supervised learning task where the output variable is continuous. Unlike classification, where the output is a discrete label, regression predicts a numerical value. Common examples of regression tasks include predicting house prices, stock prices, or temperature forecasts. Here are some key characteristics of regression. 1. Continuous output. This means the output variable can take any value within a range. 2. Predictive modeling. This means regression models aim to predict outcomes based on input features. 3. Error measurement. The performance of regression models is often evaluated using metrics like mean squared error, MSE, or R-squared. We will get into these in detail later today. So what are the types of regression machine learning? There are several types of regression techniques, each suited for different types of data and relationships. First, linear regression. Linear regression is a statistical method used to predict a continuous dependent variable based on one or more independent variables by finding a linear relationship between them, essentially drawing a straight line through data points to estimate future values. It's a supervised learning algorithm that aims to minimize the difference between predicted and actual values using a linear equation. Linear regression is the simplest form of regression. It assumes a linear relationship between the input features and the output variable. The model can be represented as this, where y is the predicted output, /beta 0 is the intercept, /beta 1, /beta 2, /beta n are the coefficients for each feature, x1, x2. xn are the input features, /epsilon is the error term. An example of linear regression in machine learning would be predicting the price of a house based on its square footage, where the square footage is the independent variable, or the feature, and the price is the dependent variable, or the target. Essentially, trying to find a straight line that best fits the relationship between the size of a house and its price, allowing you to estimate the price of a new house based on its square footage alone. Second, let's talk about polynomial regression. In machine learning, polynomial regression is a type of regression analysis that models the relationship between independent and dependent variables using a polynomial equation, allowing it to capture nonlinear patterns in data where a simple linear regression wouldn't be suitable. Essentially, it fits a curved line to the data instead of a straight line by adding powers of the independent variable as new features to the model. Polynomial regression extends linear regression by allowing for non-linear relationships. It does this by adding polynomial terms to the model. For example, a quadratic regression model can be represented as this. An example of polynomial regression in machine learning could be predicting the sales of a product based on the advertising budget spent, where the relationship between budget and sales is not linear but rather follows a curve which can be modelled using a polynomial equation. For instance, as the advertising budget increases, Sales initially rise rapidly, then gradually level off at higher budget levels, requiring a polynomial model to capture this non-linear behavior effectively. Third, ridge and lasso regression. Ridge and lasso regression are both regularization techniques used in machine learning, particularly with linear regression models, to prevent overfitting by penalizing the magnitude of coefficients, essentially reducing the influence of less important features. But they differ in how they apply this penalty. They add a penalty term to the loss function. Ridge regression adds an L2 penalty, meaning squared magnitude of coefficients. Use ridge when dealing with high multicollinearity among features, where you want to reduce the influence of all features without necessarily removing any. Imagine you're a real estate analyst trying to predict house prices based on various features like square footage, number of bedrooms, location quality, and age of the house. But you suspect that some of these features might be highly correlated, like size and number of bedrooms, which could lead to overfitting in a standard linear regression model. This is where ridge regression would be useful. Lasso uses an L1 norm, sum of absolute values of coefficients, which allows Lasso to perform feature selection by potentially setting some coefficients to 0. Lasso regression adds an L1 penalty, meaning absolute value of coefficient. Use Lasso when you need to identify the most important features in your dataset and create a sparse model by potentially eliminating less relevant features. Take that real estate example. This time you want to predict house prices using features like square footage, number of bedrooms, age of the house, distance to schools, property tax, and neighborhood type. Since some features might not be as relevant to price, lasso regression can help identify the most impactful features for accurate price prediction. So number 4, decision tree regression. Decision tree regression is a machine learning technique that uses a tree-like structure to predict continuous numerical values, essentially creating a model where data is split into subsets based on features, allowing for predictions on new data points by navigating through the tree to reach a final numerical outcome at the leaf node. It's a type of decision tree specifically designed for regression tasks where the target variable is a continuous value, unlike classification trees which predict categorical outcomes. Decision tree regression uses a tree-like model to make predictions. It splits the data into subsets based on feature values, creating branches until it reaches a leaf node that represents the predicted output. And finally 5, support vector regression, or SVR. Support vector regression is a machine learning algorithm considered an extension of support vector machines, or SVM, used for regression tasks, where it aims to find a hyperplane that best fits a continuous target variable while maximizing the margin between data points, allowing it to predict continuous values like price or temperature, rather than classifying data into distinct categories like SVM does. It's particularly useful for non-linear relationships when combined with kernel functions. Support vector regression uses the principles of support vector machines to perform regression. It tries to fit the best line within a predefined margin of tolerance, allowing for some errors. An example of when you could use support vector regression would be predicting the amount of rainfall in a city based on historical temperature data. That, my friends, are the types of regression machine learning. I hope you see how, as a machine learning student, you must choose the right type to fit the need and data. So now, how about evaluating regression models? We need to assess the performance of regression models, and we can use various metrics. First, mean squared error, or MSE. Mean squared error is a fundamental concept in statistics and machine learning, playing a crucial role in assessing the accuracy of the predictive models. It is a parameter to calculate the accuracy of the model. It measures the average squared difference between predicted values and the actual values in the dataset. Here is the formula. MSE is the mean squared error, int is the number of data points, yi is the observed value, and /bar y is the predicted value. A lower MSE indicates that the model's predictions are closer to the actual values. A higher MSE indicates that the data points are spread out more widely from the mean. A model with a lower MSE is considered better because it has fewer errors. Cool. Now second, R-squared is a statistical measure that indicates how well a regression model fits the data, essentially telling you what proportion of the variance in the dependent variable is explained by the independent variables in the model. A higher R-squared value signifies a better fit, with a perfect fit being represented by a value of 1. Here is the formula, where SSRES is the residual sum of squares and SSTOTI is the total sum of squares. A higher R-squared value signifies that a larger portion of the variation in the dependent variable is explained by the model, meaning it is considered a better fit. Also cool. Third, mean absolute error, MAE. Mean absolute error is a metric used in machine learning to measure the average difference between a model's predictions and the actual values. It's a common way to evaluate the accuracy of regression models. Here is the formula. Subtract each predicted value from the corresponding actual value. Take the absolute value of each difference, average the absolute values. Now we use MAE because it is easy to understand. MAE is a quantifiable measurement of errors. We also like it because there are clear linear changes. Changes in MAE are linear, making them intuitive. Also, there is equal weight to all errors. MAE treats all deviations from the target as equally severe. Cool. In summary, regression is a fundamental technique in supervised learning that allows us to predict continuous outcomes based on input features. Understanding the different types of regression and how to evaluate their performance is crucial for building effective predictive models. Now, I know that this is getting tougher. There are some weighty things happening here, but there are some really cool things too. If this were easy, then it would not be worth it. American televangelist Robert Schuller said, "Tough times never last, but tough people do." In other words, be tough and push through. If you do, then you're a toughie. Cheers and have a blessed day. Please like and subscribe for the sake of Tech Skill Hub and all the sweat poured out by the bits and bytes that are working hard to do this video thing. This is Ethan signing off.